Today is the beginning of calculus class. Today is like the first day. Everything has led us up to today, and it's like a new beginning. Okay? The rest of the stuff we're going to be dealing with this semester starts here. The other stuff we'll remember. The other stuff will be applied, but it's almost like we're starting again. Okay? And we left last class talking about secant lines and tangent lines. I introduced you to a tangent line. Okay? And we talked about the secant line, slope of the secant line being the average rate of change of your function over your interval. And I said, well, if we had a tangent line, all of a sudden we know what is going on exactly at that point. Okay? And we kind of thought about if we had like a table, what we needed to do to create a tangent line. You know, what could help us figure out this slope. All right, so we already did that last class. And in this class, we defined what a derivative is. All right, and the derivative, just to remind you if you didn't write it down, or if this is the first time you're hearing it, derivative is just a fancy math word for the instantaneous rate of change of something. Okay, but now this gives you a third kind of term that really means the same thing. Derivative, instantaneous rate of change, slope of tangents, all are the same. They all mean the same thing. I could be asking you a question 3 different ways, and you should just know that if you have a derivative, it's really the same thing as talking about the instantaneous rate of change, which is really just the same thing as the slope of a tangent. Okay? Interchangeable, those 3 terms. We'll find in this class there will be lots of times when we'll have multiple things meaning the same thing or one thing that could mean multiple things. Okay? And we kind of started this last class with the table, and we had a person who had positions over time. And then I asked you, how are you going to find, his velocity at the specific time? And it said, well, we needed to look maybe a little bit to the left at that time and just a little bit to the right at that time. Okay? So that's what we're going to start with in this situation. We have a function now, just a function, 2x squared. And I'm asking you what the instantaneous rate of change of the function when x is 1. Okay? And we're going to use our calculator to figure this out. Okay? But it'll be one of the few times we'll ever use our calculator to find the slope of the tangent. Okay? Now, first thing we should do is make sure we're comfortable replacing this word with derivative or slope of tangent. Okay. Second thing I'm going to introduce to you is that this entire statement can be written as just a simple expression using math notation. So I'm going to, before we start diving into that, we're going to talk about notation for derivatives. Okay. We know f of x is a function. Well, we will use f prime of x. This little tick mark we say is prime. It's just a little tick mark. It's like a 1, but it's not a 1. It's just a tick mark. Okay? And this is what we consider the derivative function, or the slope of the tangent function, or the instantaneous rate of change function. We'll start by just saying it's the derivative function. Okay. So back up to our previous question. What is the derivative? What is the instantaneous rate of change? What is the slope of the tangent of f of x when x equals 1? I could just write what is f prime of 1. This means the same thing as this entire statement. F prime of 1 is, what is the slope of the tangent of f when x is 1? All right, well, let's think about it. Here is my point 1, 2. Okay, that's important. So we need to know my function value at 1. Well, if we're talking about slope of tangents, maybe let's just kind of sketch the tangent so we can kind of see what the tangent slope's going to be. What is that slope value going to be? Positive. That's good. That's a good start. Right? Here's the tangent. We think the slope of the tangent is going to be positive. But let's go a little bit more in depth. Let's find out the actual value. Let's figure out how positive it is. Well, I need a slope formula, right? I know slope is just f of b minus f of a over b minus a. Okay? And I know I can't use the point 1, 2 in itself. I can't say, oh, what's the slope of 2 points, 1, 2, and 1, 2? I can't use 1, 2 twice. I can't go 2 minus 2 over 1 minus 1, because what am I going to get? Undefined. Okay? So you can't use kind of the point that you're located at. Okay? What do we need to do? We need to use a limit. Okay? And what is going to be our limit? What are going to be the 2 points that I could use? Exactly. Why don't we figure out, instead of 2 plus minus 2, why don't we go back and say, instead of using, f of 1 minus f of 1, let's go f of 1 minus, or let's go f of 1 plus minus f of 1 minus over 1 plus minus 1 minus. Well, if you have a calculator, you can do that. Go do that. What are you going to plug in for 1 plus? 1.00001, right? What are you going to plug in for 1 minus? 0.99999, right? No big deal. You guys can find the slope of the tangent. And the closer you get to the point, the more accurate your slope's going to be. So if I go 0.96 times and use that, that's going to be better than just 0.9, right? I'm just going to use 3 zeros and 4 nines. Let's see what I get. Got 2.0004002. And let's do the same one with 0.9999. 9996000. Okay. So I got my 2 points, plug them into my slope formula, and what did you guys get? I see a value of 2. Anybody get values that are different than 2? If you did it wrong, what did you get, Mr. Olin? 8/11. Interesting. I see a 0.4. I'm looking for positive values, right? Positive values, right? We know the slope's positive. If we're doing this correctly, we're looking for a positive value here. Might be 8/11. Let's see what I'll get. So 2.1234, 1232. Okay, that minus, so that's my f of b minus my f of a. I get that. Divided by my b minus a. I got 4. Okay, it's probably not exactly 4, right? Probably in my calculator it's 4 point lots of zeros and then some values. But your calculator eventually, after seeing the same number 10, 15 times in a row, probably tells you 4. So I got 4. Well, that's pretty good. I think I did it. I think I feel like this slope is 4. Now, I could double check if I had maybe a computer that went out more decimals. I'd probably see that it's not exactly 4. I could continue to add decimal places. I could add zeros here. I could add 9s here. And I would find out that, yes, we're going to have a slope that's 4 right at that location. Okay. Now, what's interesting to see is that I could have not even had to do 1 to the right and 1. I could have just, and 1 to the left. I could have just looked at 1 to the right and the x value of just 1. Because if you think about it, 1 to the right, 1 to the left, yes, that's kind of on opposite sides of my point, sure. Opposite sides of my point. And as they get closer and closer together, they're essentially, on top of each other. Well, that's the same thing as if I just took the point 1, 2 and used 1 to the right to it. Because they're essentially just next to each other. It would have given us the same value, okay? So cool. I just figured out how to find the tangent slope. Great. Well, what's the problem with this method? Mr. McBride, what do you think? It took a long time, A. I had to use my calculator, B. Could you have figured out the function at 1.0001 by hand, plugging that in here? No. That would have taken a long time, right? So we need a situation to find these slopes without using a calculator, without doing this process. But we're going to have to follow the similar process because, this is how we found the slope. We just 2 points really, really close together. So let's kind of generalize this situation. Can we come up with some sort of formula to help us do this without using a calculator, okay? So here's our situation. I have a random function. This is just a random function. Could look at like anything, okay? And I have 2 random points, and then connecting it is a secant line. Okay, well, we're talking about slopes. Well, let's first talk about the slope of this secant line. If this was, A and this was B, this would be f of A and f of B. I'd get f of B minus f of A over B minus A. Okay. Let's be more general. Instead of saying this first location's at A and the second location's at B, let's just say this is at any random x location on any random function. Okay, so we got x. Well, what's going to be the function value then, if this is some random point x? Mr. Johnson? F of x. Thank you. Good. Well, what I'm going to do is say, you know what, that second point, I'm not just going to make it at a random location B. I'm going to make it related to x. I'm going to give it a distance. I'm going to say this point over here, I'm going to add a distance of h to it. And all of a sudden, this point B, what is that? Just x plus h. Stay with me, Miss Page. This is good stuff. That means this is f of x plus h. Well, let's go ahead and write the slope of this secant line using the x plus h, f of x, and f of x plus h. You guys can do it with me. It's no big deal. Just instead of f of b, I'm replacing it with this, f of a, replacing it with that. Let's see what we got. So b is x plus h minus a is x. Okay, here's my secant line, secant slopes. All right, what can I do, Mr. Gibbs, that you can see algebraically with that new formula for my secant slope? Good. The x's will cancel. So all of a sudden, this can be simplified a little bit. Okay. This is still a secant slope right now. All right. Well, what do I have to do with the 2 points to turn a secant line into a tangent line? What do I have to do with this point if I want to find the slope of the tangent? I'm trying to find the slope of this tangent right here. So I'm trying to figure out, that value, essentially, but I'm going to create that tangent line by doing something with these 2 points. We move them closer together. Good. So let's think about moving them closer together. That point is going to come down and get closer and closer and closer to x. And what happens to the line? Well, the line, which started like this, will start to flatten out a little bit, and it'll become a tangent line, which is created by taking 2 points infinitely close together. Well, what do we do with h in that situation? Right, so what happened is that this started moving over as well, which means x plus h got closer and closer to x, which means h got closer to 0. So what I can do is I can say, okay, well, if you take the limit as h approaches 0, because you can't have it equal to 0, or else we're not going to have a line, okay, because we need 2 points to create a line, or we need a point and a slope. The slope's going to come from the point next to it. We'd have the limit as h approaches 0 of this, and what was a secant slope becomes a tangent slope. This is my magical tangent slope formula. This is what I'm going to be able to use to find the tangent slope of a function anywhere, so I don't have to use my calculator. Okay? This will help me figure things out. No calculators needed. This is telling me how to find the slope of the tangent of any function at any location, any x location. This is the mathematical definition of a derivative. The limits as h approaches 0 of that. Now, what's really, really important about this, because you're going to look at this and you're going to see this, and you're going to lose its meaning somehow, at some time in the future. You're going to completely forget what this means. So I'm going to make sure you know it now and make sure you can reference this page in the future. What is this? This is just a fancy slope formula. Okay? This is still coming from the slope formula f of b minus f of a over b minus a, right? We just replaced it with a generic function, 2 points. As those 2 points got infinitely close together, it turned into this. It's just slope. But it's the slope of 2 points infinitely close together. Okay? So you might be thinking, well, I still don't see it, Mr. Messner. That looks like just some crazy formula. I'm not sure how we're going to use it. I still kind of like my calculator. I still was able to find that this slope at 1 was 4, and I can kind of see it, but like, how is this going to help me? Well, let's do an example. Maybe I'll show you. Okay. Let's pretend like we don't know what 2x squared looks like. Let's find f prime at 1 this way, without a calculator, without trying to do a lot of arithmetic by hand. Let's see if we can use this magical formula to discover something. Okay? Well, we got 2x squared, and I want to find the slope of the tangent at 1. Well, let's first by writing down our magical definition of a derivative, our magical formula. That says I'm going to be able to find the slope of the tangent for any function anywhere. Well, I could actually plug stuff into this, actually. Okay? I could plug f of x in. That's 2x squared. I would plug that in. I just need to know what f of x plus h is. So let's kind of write down over here on the side. Let's remember we do have f of x, but what would f of x plus h be? Well, it's just wherever we have an x, an f of x, we'll replace it with x plus h, making sure we substitute using parentheses. Okay? Now, everybody needs to be writing this down because this is what you're going to be doing for your homework for a bunch of different types of functions. Okay? So make sure you're staying with me. All right, now that I know what f of x is and I know what f of x plus h, let's just plug it into our formula. Let's plug it into this magical equation. Let's see what happens. I have the limit as h approaches 0, so as these 2 points get close together, of f of x plus h minus f of x divided by h. Now, it's going to be very, very important that when we're subtracting f of x, make sure we're subtracting the entire thing. Use parentheses there, because if f of x is something like 2x plus 2 or 2x squared plus 2, you'd have to be subtracting that entire 2x plus 2, okay? So just keep that in mind in the future. Make sure you use parentheses and you're subtracting the entire function, okay? All right, well, this should look a little bit familiar. We've been doing problems back in the first unit that look just like this, okay? You had delta x's at some point. You had a delta x's approaching 0. For some of the homeworks, you had some test problems that were just like this. And what did we have to do to figure out this limit? Yeah, we'd have to use some algebra. So let's try to discover this limit using some algebra. So let's go. Here we go. Limit as h approaches 0, I'd have 2 times x squared plus 2xh plus h squared minus 2x squared over h. I can then distribute. What happens? That and that disappear. I can then factor an h out of my numerator. So what is this limit equal to? What is it equal to? 4x plus 2h, but it's the limit as h approaches 0. What's the last step that we have to do? Plug in the 0 for the h. So we plug in the 0, and what we get is just 4x. What does that mean? What did I just discover? I used this magical formula, and it gave me a function. What am I going to do with that? What am I going to do with a function? I want to know tangent slopes. Well, let's look back over here. Let's look at 2x squared. Are the tangent slopes at every point at 2x squared the same? No, right? So as I get further to the right, we're talking about more and more positive slopes, right? And if I come to the left, we have negative slopes, okay? They change. So 2x squared has different tangent slopes. Well, what we just discovered was my f prime of x function. What we discovered using our magical formula is a magical function. This 4x function is best friends with 2x squared. Best friends. Why? Because whenever you want to find a tangent slope to 2x squared, you can use 4x, and it is its tangent slope generator. Fascinating. Let's think. What's f prime of 1? Well, if this is f prime of x, f prime of 1 is just going to be 4 times 1. That's 4. Using our calculators, we discovered that the tangent slope at 1 was also 4. But not only did we do that, but we now have a function that can tell us the tangent slope of 2x squared at any point, say -3. Well, f prime at -3 is going to be 4 times -3, which is -12. Turns out, if you look at the graph of 2x squared, that should make sense. If I'm all the way over here at -3 and up here at this value, this tangent slope is going to be super, super negative. Okay? Well, this is really fascinating. What we have now is not only functions, but we have tangent slope generating functions. Function, and this is a tangent slope generator. Every function will have its own best friend. Some of them will share best friends, but typically we will have every function and its own best friend. Okay? So the function 2x squared has its tangent slope generating best friend 4x. We will discover that a function like, I don't know, let's talk about a cubic function. -3x cubed plus 2x, its friend that will tell us the tangent slopes of all of the points here on this function will be negative 9x squared plus 2. It's fantastic. And what is going to give us these magical functions that will tell us tangent slopes of this? Well, our magical formula, this. We can use this to discover our tangent slope generators for each function that we want to look at. Fascinating. Great. Anybody in physics C? No? Great. Good. Because if you are, then I'm going to tell you just to not talk right now and just go with it. Okay? Okay, good. Now, you might think like, all right, that's kind of weird, but I guess it makes sense. Functions will have related functions that tell us tangent slopes, but I'll kind of show you a little bit more this function relationship graphically. Okay? We're going to sketch some tangent slope functions. I'm going to move some stuff around too. I could have actually done that all at once. Haha. Okay. Everybody sketch this function.
Is that what you told us? Is that what you asked about physics C?
Right.
Okay.
If you know of a faster way, you're not going to know how to do that and not use that until after we take the test next Thursday. Yeah. So you're going to have to do this. You're going to have to use the magical formula. Okay? Okay. All right. Here's a function. Okay? It's an x-axis, y-axis, and a function f of x. We're sketching this down. What I want us to do is sketch some f prime values and see if we can discover, you know, a related function to f that will tell us all of the tangent slopes of f. All right. And here's what we're going to do. Start by sketching the tangent slopes, sketching the tangent lines at those 5 points. -2, -1, 0, 1, and 2. Sketch them. Piece of cake, right? I'll do the first. Go ahead and sketch the tangent lines at those locations. Fantastic. So this one looks like that. This one looks like that, and this one looks like that. And you can have them longer, or you can have them this short. You know you could extend them. Well, let's plot these values. Now, I don't know the specific values. I'm just going to kind of guess what they are, but I can at least see the signs of it, right? What is the slope of this tangent line? Negative, right? So then at -2, over here on the graph of f prime values, I'm going to plot a negative value, a negative y value. All right, now at -1, this slope looks to be horizontal. So what is that value for a slope if it's a horizontal line? 0. Well, over here, I'm going to plot the f prime value, or my derivative value, or my tangent slope value of 0. And I'm going to keep going. This looks to be positive, the next one. So at 0, I'm going to place a little positive value. Here, it looks like I have another 0. So I'll go back down to 0. And here, we have a negative value. Does it look like we've created some sort of shape of like a function that is familiar to us? Yeah, parabola, right? Well, do you think it's okay for me to connect these dots and kind of extend? I don't know, maybe it is. Let's check. Who knows? Let's check at, 0.5. If I check right over 0.5, so that's the tangent slope here, I see I have that tangent line. Now, this slope right here, is that going to be more positive or less positive than the slope here at 0? Less positive. Okay, so that means between 0 and 1 at 0.5, I will have a less positive slope than at 0. Okay, I could do the same thing at negative 0.5. I have a less positive, and all of a sudden we can see that, yeah, you know what? If I continue to do this process, we're going to fill in all these dots, and we are going to be able to just go, bloop. This is a function. This function can tell me all of the tangent slopes of my original function. It's kind of its neat little partner. If I want to find the tangent slope of f at 2 and let's go negative 1.5. At negative 1.5, I see that f prime should be negative. Well, I go to negative 1.5 and I see that my tangent slope at that location is negative. So fascinating. And what we will discover, and while we do this more, is that, if we have some sort of cubic function, I don't know what exactly it is, its partner, its slope generating partner, is going to be some sort of quadratic function. Don't know exactly what it is, but they are related. Very interesting. Let's see what happens when I have a parabola. So this parabola is all in the first quadrant. So I'm just looking at the positive x values, 1, 2, 3, 4, and 5. You guys go ahead and sketch the tangent slopes and then plot the tangent slope values over here on an f prime graph. Now, it's important to not only think positive, 0, and negative, but like you can think about, values in terms of this is more positive than this, or this is more negative than this, and you can compare the values. That way you're not just saying, oh, the first one's positive, second one's positive, you're putting them in the same location. Think about larger values, smaller values. And then compare your answer with a neighbor. Good. All right. Okay. Excellent job, everybody. Good. Good. Did you already watch this or something?
I watched the video, the end of the video, the last one.
Right. Gotcha. Okay. Cool. Cool. That's okay. You're good. You're good. Positive, less positive, 0, negative, more negative. Fascinating. And if I connect, and I can connect if I just kind of examine more, that my buddy, my friend of my original quadratic function is going to be a linear function. And this linear function can tell me the tangent slopes at any point of my original function. So it's fascinating. We'll have functions for tangent slopes. This is like an x squared, some sort of, this is like an x, but it's like some sort of mx plus b. Yes, Mr. Olin.
Is the derivative graph of the sine graph, whatever that is, parabola, or is it?
We'll get there. We'll get there. We'll discover it. It's actually, it's kind of cool who sine's friend is, who tells him all of his tangent slopes. We'll get there. What about a line? if I have a line, who's the line's friend? Is it going to be the same line? It's going to be a straight line, horizontal line, because the slope is the same everywhere for a line, right? So the tangent slope is just going to be the slope value of the line. Okay, if this is equal to -3, we have all negative values. All right, so here is the line's buddy, a horizontal line. All right, and we can see this graphically, this relationship. It's pretty cool that we have these relationships and we have these functions and their derivative generating friends. Okay. Now, key things to remember. This is especially when you are developing equations of tangent lines, because we're going to go back to our previous example, that if you have a function, you'll plug in x's, you get y's. You get points on your function. Well, this f prime, this friend of f, who tells us the slopes of f, you plug in x's, sure you get y's of f prime, but you also get slopes of f. Get tangent slope values of f. All right. So back to my previous problem where I discovered this, friend of 2x squared. The friend of 2x squared is 4x. He's going to tell him all of his tangent slope values. Well, we already figured out the derivative of this function when x is 1. Just we're able to now plug in values into this friend, and we will figure out tangent slope values. But we can even go a step further and find the equation of the tangent line. Okay, so here we go. What is the equation of the line tangent to my function at 1? Well, let's remember what we need for a line. I need a point and a slope. Where's my point? Well, let's think about it graphically. If I have 2x squared, looks like this. Okay, I need the point on my function. That's the tangent location. That's where we are going to have our line. So the point is going to come from f of x. And I found out f of 1 by plugging in 1 into my function. This is what everybody forgets, and that's 2. But I need the slope of this line. Well, the slope of the line will come from its friend, its derivative, that will tell him the tangent slopes of the function anywhere. And I know that f prime, using my magical formula, was 4x, and that means f prime of 1 is equal to 4. Now that I have my information, I know this line's equation is y minus 2 equals 4 times x minus 1. And now, using technology, we can see both the function and its tangent line. Let's go to y equals. We have 2x squared plugged in. If I solve this for y, I have 4 times x minus 1 plus 2. I'll just write it just like that. Don't even have to simplify it more than that. Plus 2. And we should see 2x squared, and then its tangent line at 1, 2. Awesome. Okay? All from a magical formula. Well, why don't you guys figure out the equation of the tangent line to my function when x was -3?
We can leave it as y minus 2.
Yeah, of course. Simplify only for multiple choice questions or if you have to graph it. Okay, do it. What is the equation of the line tangent to the function 2x squared when x equals -3? And if you had your calculator, you could graph and check and see if you're correct. What's my point, Mr. McBride? Is it -12? No. That's my slope. You're right. My slope, f prime at 3, -3, is -12. Does that go where this goes and this goes? Where does this go? For the slope. So -12. What do I do with my y1 and my x1? Where does that come from, Mr. McBride? Yep. You just plug in x there to get my point on my function here, -3, 18. And that would be the equation of the line. That would be right there. And if we graphed it, we could see it as well. We got 4x plus 1 already. Let's go ahead and graph this other one. -12x plus 3 plus 18. Graph. Voila. At -3, 18, there's my tangent line. Okay? Cool. Well, that's just for 2x squared. We focused a lot about 2x squared. There are other functions, and they have slope generating function friends as well. And we're going to need to find these slope generating friends. And we're going to start this one. And there's going to be another one that I'm going to show you on the video. And I'm going to show you how your friend, the formula for the tangent slope of anything, sometimes is really annoying to work with. There's lots of algebraic steps, but it will work. And then after we take our test, we are going to learn that we don't need to use this magical formula. We can just kind of throw it away and use rules. But we're not there yet. So let's find the equation of the tangent line to the square root of x plus 1 when x is 3. Step 1, start out with your magic formula. This is going to produce our tangent slope generating friends for any function, which will then tell us tangent slopes at any point. I need f of x and f of x plus h. Well, f of x is root x plus 1. I know that. What is f of x plus h? Now, this is important. If there was another x here, you would have to substitute x plus h in wherever you saw x. So this f of x plus h would be the square root of x plus h plus 1 plus another x plus h. Okay, so keep that, write that down as a note so you don't forget it. However, in this situation, we don't have that other x, we just have the root x plus 1. But remember that. If you had an x at another location, you have to plug in x plus h at those other locations. Okay, now that we have that, we're going to go ahead and plug it into my magical formula that we generated. We have the square root of x plus h plus 1 minus square root of x plus 1. over h. What do we have to do now to find this limit? Can't square everything. That's going to change what I have. You square everything, then all of a sudden you will change what you started out with. Mr. Thomas, what do you think?
Multiply both the top and bottom by square root of x plus h plus 1 plus square root of x.
Yes. What is that C word that you are doing? Multiplying by the conjugate. It's 216. Hold on. We still have a minute. This is crazy. So you will multiply by the conjugate. Wait till it turns 217. And then what you will do is you will watch the video to see what happens from there. And you need to make sure you watch it because I'm not only going to show you the rest of this one, but I'm going to show you another one with a common denominator that we'll have to find, okay? And those are the tricky problems on your homework. All right, so let's multiply by the conjugate. We would get x plus h plus 1 minus the quantity. Make sure we use parentheses, x plus 1, all divided by h times that conjugate we're multiplying, x plus h plus 1 plus root x plus 1. And this is the limit as h approaches 0. Now I can distribute this negative. There we go. I can distribute this negative. This is going to be negative x and negative 1. And I notice that both of my x's will cancel, 0, and my 1's will make a 0, leaving me with just an h in the numerator divided by the h times root x plus h plus 1 plus root x plus 1. The h's will cancel, and now I can find my limits as h approaches 0 of 1 over root x plus h plus 1 plus root x plus 1. And the last step, remember, is to take 0 and plug it in for h after you've simplified and gotten an easier function to work with. So once I plug in 0 for h, I'd get root x plus 1 plus root x plus 1. Well, that is going to be 2 root x plus 1. And what we've discovered is our magical slope-generating function, f prime, which will tell us the slopes of f no matter where we look. Okay, so this is great. We have root x plus 1's friend, this guy. The question, back to the question, was what is the equation to the tangent line of this function when x is 3? Okay, so I need my equation of a line. Don't forget for your equations of lines, you need your point. Well, the point is going to be the point on my function where the tangent line is passing through, you know? So the point is going to be coming from my function value, f of 3. Well, that's root 3 plus 1, which is 2. Now the slope of my tangent line will come from my slope-generating function, f prime. So I'll be able to find f prime of 3, 1 over 2 root 3 plus 1, so that's 1 over 4. Well, now I can write my equation, y minus y1. This will be my y1, this is my x1, and this is my m. Y minus y1 equals m times x minus x1. And if we graphed both root x plus 1 and we graph this, we would see that this is a tangent to root x plus 1 at 3. Good stuff. Next one. Let's see if we can find the equation of the tangent line to the function 2 over x plus 3. Okay, well, I'm going to use my guy. And we need to figure out what f of x plus h is. We know f of x is 2 over x plus 3. F of x plus h is 2 over x plus h plus 3. So that's what it'll be like. Whenever we see x, no matter if I had another x somewhere else, I'd have to plug in x plus h all of those places. So I want the tangent line when x equals 1. Let's first find my tangent slope. Generator. Plug in x plus h. There's f of x. All over h. And after this, I'll probably just multiply everything by 1 over h, just so we have things that are simple. Now, how do we get a common denominator? Well, the common denominator will be, you think you can, can I just add h to the bottom and add h to the top? But that is not allowed, okay? That is changing something. You're not allowed to multiply something by a number. You're allowed to multiply, you're allowed to add by, you're not allowed to add a number to something because that's going to change it. You're allowed to add 0 to something, but I'm not allowed to add anything other than 0. So I need to multiply by versions of 1 so that I don't change anything. So this is where we're going to have to just multiply the other fraction by the other denominator. So like I would multiply this by x plus h plus 3, and this x plus h plus 3, and this one I'd multiply by x plus 3. Let's see what I get. I get 2x plus 3. I'm going to go ahead and just distribute on the numerator. So 2x plus 6 minus 2x plus 2h plus 6. And that's going to be this entire quantity that I'm subtracting. And now I have my common denominator that I can put everything over. And then when we multiply by 1 over h, that's like dividing by h, or I could just move this h into there, and now we have that. Let's see what happens. This becomes a negative 2x, a negative 2h, and a negative 6. When I distribute the negative, the 2x's will cancel. The 6 will cancel as well, just leaving me with the limit as h approaches 0 of negative 2h over x plus 3, x plus h plus 3, and h. And I can actually cancel this h. And when I plug in, after I cancel the h, I can plug in 0. And I get negative 2 over x plus 3 times x plus 3. So that is negative 2 over x plus 3 squared. And that is my friend to 2 over x plus 3, negative 2 over x plus 3 squared. It's very related to it. Okay, and if I want the equation of the tangent line, I need my point, which will come from my point on my actual function. That's 2 over 1 plus 3, so that's 1/2. And I'll need my slope. That'll come from my tangent slope generator. Negative 2 over 1 plus 3 is 4. 4 squared is 16, so that's negative 1/8. And then here's my equation. Y minus y1 is equal to m times x minus x1. Great. Now, one thing we need to talk about is, are there situations when we cannot differentiate? Yeah. And like other situations where tangent slopes do not exist. And you should just think about this graphically. And I'll just show you graphically. On what graphs could we not have a tangent slope? Well, the first thing you should be thinking and considering is if we have a discontinuity. If I have a situation where I have an asymptote, well, I'm not going to be able to put a tangent slope at this location A. So immediately I'm just saying, well, I'm not differentiable at A. And what does not differentiable mean? I can't place a tangent slope. Okay, what else? Well, if I have a hole, I'm not continuous, I would not have a tangent slope there. So whenever we have a discontinuity at A, we're not going to be continuous. There are other situations where we have cusps we would not have a tangent slope at this location at the cusp, and this is called a cusp. Or if I have a sharp point, like a absolute value graph. We would have tangent slopes everywhere else, but at the location of this sharp point, we are not differentiable. Okay, but we have tangent slopes everywhere else, and it's kind of makes sense. You can't really draw a line that is going to mimic your function right at the point, so you're not going to be able to find that tangent slope. And the reason why is we can only differentiate when this limit exists. Well, let's talk about limits existing. When do limits exist? Limits exist when the left-hand limit equals the right-hand limit. Well, if we're thinking about this limit, in this formula, this is really just slope, right? This is like the slope formula just of a special situation. And as we take the h and approaches 0, then we have the slope of 2 points that are getting really, really close together at some x value. Well, if the slopes from the left equal the slopes from the right, then we're going to have a limit. If they do not equal each other at the location of this cusp, the slopes are negative and then they're positive. They do not equal each other. Location at a cusp, these slopes are getting more and more positive from the left, and they're getting more and more negative from the right. Since the slopes do not equal each other, then that's why we would not be differentiable. Okay? So situations where we have discontinuities, cusps, sharp points, those are locations where the derivative does not exist. Okay? And that's it. Thank you.